right, it's time to start class. It's 1:50. Let's see. What's happening next Tuesday? We have a midterm. We have an exam, right? It's going to cover up through 4.1, supposedly. What time is the exam? 7:05. We'll get here early. We'll start on time. We'll end on time. Not here. Yeah, it's not here. It's in Campbell Hall, 200, just like last time. What questions do y'all have? Or what should we do on Monday? We should review on Monday. So if you have questions and you want me to give you good answers, you should send me an email. Didn't you have like some relay rates problems you wanted me to do? Yeah. You got those answered? Maybe some of these other people would like to see in it. Okay. I don't know. Well, if you have questions and you send me an email, I'll give you a good answer. If you just ask me on Monday, who knows? I might just say tough. I don't know. Make sense? All right. What questions do you guys have before we start? Oh, let's hear the question, then I'll tell you. I'm sorry, I'm going to make you ask me the question first. She has a question about 25 in the book. Let's see, do you have it with you? I have it with me too. Yeah, why not? Let's try to do it, okay? Hopefully I don't do it wrong. All right? Or better yet, you know what we'll do? All right, everybody try to do number 25 in the book. On Monday, I'll do it, and we'll make sure that it's all good. That way, make sense? Even if you have the answer, I'll still do it, unless you have another question. All right? Oh, and if you guys have questions at any time, just shout it out. Seriously, because I get overwhelmed looking at everybody in the classroom. It's weird. I can't see everybody. I won't mind. All right. So today we're supposed to cover 4.2. And this chapter is mysteriously called What Derivatives Tell Us. So what is the derivative? Oh, wait a second. Before I say this. Oh, yeah. I don't care if you guys did really well in the first exam. You have to study for this exam if you want to do well again. It's a fact. And you got to make sure you can take derivatives like this. You got to be an expert at derivatives. The only way this is going to happen is if you practice taking derivatives. You can't looking over your notes really isn't going to help. Watching me do stuff, to be honest with you, isn't going to help. It'll help maybe a little bit. The only way for you to get good at this is practicing yourself. We've got some practice problems, I think, posted on Carmen, and there are practice exams posted on Carmen, and there are practice derivative rules. Now you might say, how do I know if I did it right? There are online places that you can just type in functions and say, give me the derivative of this, and it will tell you the answer. Or you can email me. That'll be a disaster if everybody emails me. I'll just never get anything done this weekend, but you can. Or you can email your TA or whatever. But you have to practice. You have to do it yourself. That's what you have to do. I want everybody to do well on the exam. And I think that's all I have to say about that. It will be about like the last exam. You're going to have to work fast. You're not going to be able to sit there and think. You have to basically have done the problems before, right? You won't be able to sit there and think, well, this is an interesting question. I wonder how I solved this problem. No, that's not how it is. We just expect you to produce. All right. So, the derivative. The derivative is the slope of the tangent line, right? It's the slope of the tangent line to the curve. It's the slope of the tangent line to the curve. And if you know what slope means, and if you know what tangent line means, then really I think you can do almost, this next stuff isn't hard to understand. Now, that's one thing, here's something you need to know. A critical point what's a critical point? Yeah? It's where the derivative is 0. You know why you need to know this? Because if we ask you find all critical points, and you don't know what a critical, or wait, it's where the slope is 0, where f prime of x equals 0, or f prime of x is undefined. Better yet, let's say it this way, does not exist. I don't know why that's better. We'll say it that way. F prime of x equals 0. And this is important because it wouldn't surprise me if on the exam we say find all critical points. And you're like, oh crap, what are critical points, right? If you don't know what they are, if you don't know that there's these two parts to it, this one most people remember. This one not as much. So remember this too. You're stuck. Okay, so critical points, and why would anybody care about critical points? Minimum or maximum? There's a classic problem in calculus, and if I was feeling really gutsy, I'd try to solve it for you because I want to know the answer. I'm not sure if you always see me fiddling with the camera. There's a best place to put that camera where we sort of maximize the angular size of this board, right? Where we can kind of see the most and we want it to be as big as possible. And so I've been trying to move it over. Right now we have from here to here. And I'm thinking about, from your viewpoint, when you can see the most. So there's some sort of max-min problem on where I put that camera. And why haven't I solved that calculus problem for our calculus class yet? That's because I've been busy and I keep on forgetting to. But, I should try to solve that one. And maybe if you guys don't have many questions, if I do, you don't have any questions on Monday, I'll do it in class, maybe. Maybe. Anyhow, so you want to know about maximums and minimums. You want to be able to maximize gas mileage. If you have an airplane, you want to be able to minimize drag, that sort of thing. If you're a speed walker, you also want to be able to minimize drag, right? You could wear like some sort of whatever. So you can that's why critical points are important. Now, there's something called the first derivative test, and to be honest with you, I'm a mathematician, but I don't do calculus all that much, and I had forgotten what it was. And then when I read it, I rolled my eyes. So the first derivative test, and this I don't think you need to know word for word. This you just need to understand. Critical points, you have to know what they are because we might ask you for critical points. Oh, it's just where the derivative equals 0 or doesn't exist. Yeah, but if you don't know that, you can't answer the question, where are the critical points? You've got to be able to know what critical. The first derivative test, if you understand it good enough, you don't need to be able to regurgitate it. And it's so simple in some sense, you can simply understand it. So it says, if f prime of x is greater than, so we have f prime of a equals 0. F prime, so a is a critical point, right? X equals a is a critical point. Okay? And now the first derivative test is almost, I hate to disparage the subject, but it's like the stupidest test ever. Okay? It says that if f prime of x is positive for x less than a, and f prime of x is negative for x greater than a. If it's positive for x less than a and negative for x greater than a, what's that tell you about the point at f of x equals a? It's a maximum. Then A, f of A, is a local maximum. And I say it's a silly test because if you know what the slope of the tangent line means, if f prime of x is positive, then f of x is increasing. If f prime of x is negative, then f of x is decreasing. You can recover this. You know, you don't need to know it's called the first derivative test. It's nothing super fancy. And likewise, so there, let me draw a picture. Boom, boom. F prime of x is greater than 0. F prime of x is less than 0, right? If f prime of x is negative for x less than a, so it's negative for x less than a, and f prime of x is positive for x greater than a, then a f of a is a min, a local min. And then here's your picture right here. F prime of x is, we're decreasing. The slope of the tangent line is negative, less than 0. F prime of a as x is greater than 0. This is not something you should memorize. This is something you should just understand. You should think, okay, when the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. Does this make any sense to anyone? Okay, some people are saying yes, that's good, good enough, right? All right, so that's the first derivative test. All right, that's good enough, yeah. Yeah. Oh, okay. Well, okay. Let's do an example, I guess. All right. All right, guys. Okay. So are we ready? Are we cool doing an example of this? Yeah. Okay. All right. Meh. I don't know why I did this. Okay. So. All right, so here's the example. F of x equals x to the 4th over 4 plus x cubed over 3 plus x squared. There's our function. And find the intervals. Find intervals where f is increasing, decreasing, and find a local extrema. All right, so this is a 4th degree equation. First thing we're going to do is take the derivative. So f prime of x is equal to, what's 4? Oh, that's equal to x cubed plus x squared plus 2x, right? X cubed plus x squared plus 2x. That's the derivative. So we want to find, step 1, find the critical points. That's where the derivative is 0 or undefined. So let's see, well, we got to say x cubed plus x squared plus 2x is equal to 0. It's a cubic, but what can we do first? Factor out an x. So it's going to be x times x squared plus x plus 2 equals 0. Aha. So one critical point would be x equals 0, right? Because if x equals 0, then this thing's 0. All right, so now I'm going to forget about this one and just solve x squared plus x plus 2 equals 0. Aha, it's a quadratic equation, right? I can use the quadratic formula. Can we factor this? Yeah, I think, well, I don't know. Can anybody factor this for me? X plus 2 minus 1? X plus 2. Well, that's negative 2. Nope, can't factor it. OK. So now what? Oh, shoot. Make that a minus sign. Make that a minus sign. Make that a minus sign. Make that a minus. OK, now, I'm sorry. I'm sorry. I'm sorry. I'm going to give you guys a second to recombobulate yourselves. And I will think about the mistake I made. No, I looked at it and I said we're going to have complex answers to this, which means we don't have critical points, which means this example is pretty stupid. Bart, were you really that stupid to write down that example? I said, no, just now. OK, now we can do it. And look, her factorization really works pretty well, I believe. She knew what we should write down. She says it's going to be x plus 2 times x minus 1, right? All right. So x is equal to minus 2, or x is equal to 1. And so my other critical points are x equals minus 2 or x equals 1. And so what really is nice to do here is you make what's called a sign chart. A sign chart. This is where, remember, these are where the first derivative is 0 or undefined. So you make like one of these things here, and you put 0 down here, and you put 1 here, and you put minus 2 here. You make some lines like so. And you just ask yourself, is the derivative positive or negative on those intervals, right? OK, so and you try to plug in easy numbers. You try to plug in easy numbers. So this one looks easy. What number is between negative 2 and 0 that's easy to deal with? Negative 1. OK, and so now let's look at the first derivative. Here it is. Plug in negative 1 here. I'm going to get negative 1 plus 1. That's 0. Minus 2 times negative 1, which is 2. And so the first derivative, f prime of x, is positive here. OK. Now let's think about this area right here. What's a number between 0 and 1 that's not too bad? 0.5, right? What's 1/2 cubed? 1/8. 1/8 is a number close to 0, right? What's 1/2 squared? 1/4, right? 1/8 plus 1/4, is it bigger than or less than a half? It's less than a half. So this piece is going to be less than a half. And then it's going to be minus 2 times a half, which is negative 1. So when we have a half here, f prime of x is going to be negative. I didn't actually calculate what it was going to be. I didn't need to. I just decided, is it positive or negative? So now, what about past 1? Well, 2. 2 is past 1. 2 cubed is 8. 2 squared is 4. 8 plus 4. I don't care what it is. It's positive. It's still positive after I subtract this off, right? So positive f prime of x. And then over here, negative 3. That's a good one. Negative 3 cubed is negative 27. And that's going to make this whole thing negative. F prime of x is negative right here. Right? That looks good. Yeah. So here, our function is decreasing. Here our function is increasing. Here our function's decreasing. And here it's increasing. Decreasing, increasing. If it's decreasing, then increasing, is this a max or a min? It's a minimum. So this is a local min. And this is going to be, it's increasing, then it's decreasing. So this is a local max. And now it's decreasing, and then it's increasing. This is a local min. And so our function looks something like, I'm not going to make any claim that this is exactly right, but I'm going to say that our function looks something like, if we were to plot it, it's decreasing, increasing, decreasing, increasing. Our function looks something like that. Something. It actually crosses the x-axis, but that's not a big deal. What questions do you have about this example? Do you want to ask? Come on. She's asking a great question. She says, you know, Bart, you said find intervals, but you never found any intervals. Why don't you tell me some intervals? Yeah, let's write down the intervals. Now, we don't care. She said, you can write it. I'll give you two different ways to write this. Both are correct. All right, so let's give the final answer. I drew some crappy sketch. Sorry. Let's see. The intervals are going to be minus infinity to -2. The function is decreasing. You could also write, if you're more comfortable with minus infinity less than x less than -2, if you're more comfortable with that, that's perfectly fine. All right? -2, 0, the function is increasing. Zero, 1, the function is decreasing. And 1 to infinity, the function is increasing. Hey, you two ladies there should be quiet. Yeah, you two. Shh, I can hear you all the way up here, and I can't hear anything. Okay? You might be disturbing somebody else in this class. All right, yes? You're still talking. I can see you. Shh. Quiet. Go ahead. She says, if you want to write increasing and then list all the intervals, do you need to put a union? No, we'll know what you mean. Okay, like it's increasing on this one, and this one. Perfectly fine, okay? What are the local extremum? That's the local min, local max, local min. Good? All right. So that's the first derivative. Now, if we take the derivative again, we get more information. And so here I'm going to draw a handy chart that I don't know this might be useful to write down. I guess if I was in this class, I'd probably write this down. All right, so we have, this looks good, and we're going to put f prime of x is less than 0, f prime of x is greater than 0, f double prime of x is less than 0, f double prime of x, oh shoot, that's greater than 0, I'm sorry, is less than 0. There we go. So, if f prime of x is less than 0, what's that tell you about the function? It is, yeah? Yeah, go ahead.
Two absolute mins, like if the lowest point on the graph is the same. You know what I'm saying?
He's asking what happens if there's two absolute mins. You write there's two absolute mins. Yeah, sine has like an infinite number of absolute mins. Yeah, you can write that. Let's hope we don't do that to you, because that's just... I hope we don't do that to you. If we do, I apologize in advance, okay? But you just write there are two absolute mins. All right, but if f prime of x is less than 0, what's happening to the function? It's decreasing. So our function is decreasing. I'm going to use the negative chalk to show you there's the decreasing function. And if the second derivative is greater than 0, that's telling you that the function is decreasing at a slower and slower rate because it's getting more positive. And so it looks like this. That's what your function looks like. This is called concave up. Concave. You guys, we all remember how to remember concave, right? Because it sounds like a cave. A cave's like a hole, right, that you live in. So this is the cave part, and the cave part is up. Concave up. Concave up. Concave up. Now here, the function is, the derivative is positive, right? The derivative is positive, so it's going like this. So the function's going like so. And it's getting more and more positive all the time because the second derivative is also positive. The derivative of the derivative says that the derivative is increasing. So it looks like this. Also concave up. Concave, you got a little cave shape, and the cave shape is up, right? As opposed to what we're going to draw next, concave down. So let's see. F prime of x is less than 0, so f of x is decreasing. It's going like this, right? Decreasing. And f prime of x is less than 0, so it's decreasing faster and faster, right? So it looks like so. And so this is the concave part, and it's below the curve. Concave below, concave down, right? Concave down. And then here, the derivative is positive, so it's increasing. It's going from left to right and up. But it's increasing at a slower and slower rate. So it's going to be concave down, but this way. So here's the cave part. The cave part is below, it's down. Concave down. And so the second derivative here tells us more information about what the curve looks like. Hopefully this can help. Now, we have a test for concavity. A test for concavity. What questions? Does anybody have any questions about this? All right, so test for concavity. Yeah, we're not going to write it down because it's stupid. The test for concavity is this right here. What's it tell you? If the second derivative is positive, then it's concave up. If the second derivative is negative, then it's concave down. Up for positive, down for negative. Right, okay, there, done. Okay. Aha, so now the critical point has a cousin, call it an inflection point, but the inflection points are a little different. So inflection point. If there was any justice in the world, an inflection point would be where the second derivative is 0 or undefined. That's not right. All right? An inflection point is where the concavity changes. So it's where the concavity changes. Where the concavity changes. And let me draw you some examples just to kind of explain that it's upsetting to me at a deep level, maybe not that deep a level, that an inflection point is where the concavity changes and not where the derivative is 0. So check this out. So inflection points will be in pink. Well, boom, boom. This is an inflection point. It goes from concave up to concave down. Very nice. On the other hand, not an inflection point. The second derivative is still 0 here, but it's not an inflection point. The second derivative is 0 here, but it is not inflection point. I think they did this just to confuse students. See, critical points are where the first derivative is 0 or undefined. Do you necessarily have maximum or minimums at critical points? No. Inflection points are defined the other way. They're where the concavity changes. So they will be 0 or undefined, but just because the second derivative is 0 or undefined doesn't mean you have an inflection point. You have to look at the picture. So let's see, here's another case. You could get something like this. This is an inflection point. Here we go. Inflection point time. There, that is an inflection point. That's an inflection point. So that goes from concave up to concave down. If you were doing a sign chart for the second derivative, it'd be exactly the same because the sign of the second derivative, when it's positive, means concave up, concave down. That's right. So you have to have the signs changing to have an inflection point. So here's the problem. Inflection points are not critical points of the first derivative. Well, actually, inflection points are. The inflection points are a subset of the critical points of the first derivative. But there are critical points of the first derivative that are not inflection points. Yeah, you think about that for a while, okay? Think about that. And I think it's, yeah, anyways. Okay, in blue, here's another example of not an inflection point. And this is basically all the ways it can happen. Not an inflection point. So something like this is like x cubed, or actually negative x cubed. Right? Something like this is like negative x squared. Something like this is like arctan of x. And something like this is like x to the 3 halves. Is that right? Yeah, that's right, x to the 3 halves. X to the 3 halves. Yeah. How about x to the 2/3? Yeah, x squared, yeah. So this is like x to the 2/3. Not an inflection point. Oh, and the points I'm talking about are this point, this point, this point, and there. That point right there. Yeah. All right, was that good? I think that's good. So, inflection point, oh, this is confusing. Non-inflection points help us find maximums or minimums. Look at this. Is this a maximum or a minimum point? Right? Is this a maximum or a minimum point? Is this a maximum or a minimum point? Yes? Is this a maximum or a minimum point? Oh, it's a minimum. This is a minimum. Okay, so this is our so-called second derivative test. Which is a good test. Second derivative test is an awesome test. The second derivative test says that if f prime of x equals 0, right, Bart, right. And f double prime of x is negative for is negative at, oh geez, okay, f prime of a equals 0, f double prime is negative at a. Yeah. Then x equals a is a, so it's negative, so that means it's concave down. X equals a is a maximum, local max. And likewise, if f prime, double prime of a is positive at a, then x equals a is a local min. If f double prime is positive, that means it's concave up. It looks like this, right? And if f double prime is 0, of a equals 0, then you cannot tell. At least not with the second derivative test. Then you need to plug in points. You need to do something more sophisticated. Okay? The test says nothing. It could be a local max. It could be a local min. It could be neither. All right, let's continue our example from before. Let's do that. Yeah. Let's do our example from before, but let's just make it easier. So you can always, look, if I was taking a test and I knew all these, if I knew all these second derivative, first derivative tests, and if I'm allowed to use whatever I want, what I would do is I'd take the first derivative, I'd take the second derivative, I'd try to find where the first derivative equals 0, and then I'd try to use the second derivative test. If it works, great. I know where the local maxes, know where the local mins are. If it doesn't work, then I try to identify where the first derivative is positive or negative. If for some reason that doesn't work, that should always work. Okay, that should always work. You can just plug in random points and see, like, you can try to figure out what's going on there. But really, working with the derivative is often easier than the function because you're usually dealing with polynomials. And what does the derivative do to a polynomial? It lowers the degree. And usually, I mean, here's like the standard thing to do on a calculus test. We give you a 4th degree equation that you can't solve because you probably don't know the 4th degree formula. And then you take the derivative, and it gives you a cubic that you can factor, just like the one we did, right? And then you factor it out, and then you use the quadratic formula on the quadratic part. This is like a standard thing to do, So we can't give you a 7th degree equation, because when you take the derivative of a 7th degree equation, what's going to happen? Well, we can't give you a generic one. Like we can put bunches of x's in there. It's going to go down to a 6th, and you probably can't solve a 6th degree equation unless you can factor something out. All right, let's do an example. Example time. Yeah, but I seem to have lost all the erasers. They're both over here. Okay, so we're going to do this. I still like this example a lot, this one right here. So we have f of x equals x to the 4th over 4 plus x cubed over 3 plus minus x squared. F prime of x equals 0 when x equals -2, x equals 0, and x equals 1. Is that correct? Awesome, that's correct. All right, so now if we want to do the second derivative test, we got to take the second derivative of this thing. Okay, well, the first derivative, which I've forgotten now, is equal to x cubed plus x squared minus 2x. And the second derivative is 3x squared plus 2x minus 2. And so if we want to do the second derivative test on this, what we do is we plug in these points to the second derivative. No solving, just plug in points, find out what they're equal to. So let's see. F double prime of -2 is equal to -2 squared is 4. 4 times 3 is 12. I don't care what this is. -2. Oh, it's -2, I guess. 4 times 12 minus 4 minus 2 more. It's positive, right? What's that tell you about this thing right here? If it's positive, the second derivative is positive. It's concave up. So this has to be a local min. What's f double prime of 0? Ooh. It's 0. What's the second derivative test say here? It doesn't say anything, right? We're out. I don't know. Question mark. Let's keep on going. It's because it's -2. No, my bad. Sorry. Thank you for correcting me. I was plugging it into the derivative again. So this is negative, so it's a local max. Woo! And f double prime of 1 is equal to, it's positive, right? Local min. Good? What questions do you guys have? Oh, which of these are inflection points? Good question. So he says, let's find the inflection points of this curve. All right, let's do it. So first of all, what you can do is you can start to sketch the curve at this point. I'm going to erase the second derivative test. I think we can remember it. To be honest with you, the second derivative test follows directly from that picture eventually. So, I mean, that picture is a good picture. So what you need to do is you need to start plotting here. And so we have x equals -2. So here's -2. And then here's 0. And then here's 1. And let's see, I took the second derivative, so I know that f prime of x, I have this, and I know that that 2 is a local minimum, right? So I can kind of imagine my function doing this, like this, and then here, right? And then here to get another local minimum. Right? This is from the second derivative test. So now, now I need to see where the second derivative equals 0, because that's the only time that concavity can change. But that doesn't mean that those are inflection points. It just means that that's the only time. And the second derivative is, let's see, oh, it's this nice equation here. So f double prime of x is equal to 3x squared plus 2x minus 2. Can anybody tell me when this equals 0? We could use the quadratic formula, right? That'll work. So x is equal to, what's it equal to? Something over 2 times 3. Oh, geez. I have an a in here. I almost never have an a. So -2 plus or minus the square root of 4 minus 4 times -2 times 3. Is that correct? That is correct? I think so. Negative b plus or minus b squared minus 4ac all over 2a. All right. So x is equal to something over 6, -2 plus or minus, let's see, this is going to be 4 minus -24, right? And so this is going to be 4 plus 24, so I get 28. 28, 2 plus or minus 20, square root of 28 over 6. Oh my God, square root of 28. Does anybody know how big that number is? Let's see, 5 times 5 is 25. 6 times, it's just a little bit over 5. So this is a little bit over 5. So it's -2 plus 5 is 3 over 6. So this is going to be, so x is approximately 1/2, and x is approximately, let's see, I lost my plus or minus. -2 minus 5 is going to be -7. So what, 7 over 6 is like, I don't know, negative 1.16 repeating or something like that. Around there. I'm just making those numbers up. All right. But this looks good, right? Because look at what's happening here. This is suggesting that concavity is changing right here. And it's suggesting that concavity is changing right around here at minus 1.6. And if you think about what this curve should look like, that makes sense that concavity would be changing right around here. So how do we figure out concavity changes? Well, we plug in, we see if the sign of the second derivative changes. What is the sign of the second derivative at negative, what's the sign of the second derivative at negative 2 again? The sign of second derivative at negative 2 is positive, right? And the sign of second derivative here is negative. So yeah, there's going to be an inflection point right here. There's going to be an inflection point. We found where it is 0. If we had better numbers, there's going to be an inflection point here. So your curve, and there's also going to be, here it's negative, and here it's positive. And so these are the only choices for inflection points. The concavity does change. And so your curve, don't use pink, the curve is going to look something like this. It's going to be like that, then like that, like this, like this, then like that. That's a terrible drawing. Looks like an octopus. But there we go. So that's the sort of idea that you have. Now, yeah? They're approximately 1/2 and negative 7/6. The inflection points are where the concavity changes. And if you have an inflection point, the derivative will be 0. My alarm's going off, so you guys have a nice weekend, okay? See you guys on Monday. We'll review. If you have questions, ask. Send me an email.